All right. Hello. So, welcome to the first time I've ever even come close to attempting this train wreck of a remote dissertation defense. Y'all have any experience with this, Dr. Ferry or Hammond?
I've done a few. I don't know about Frank, but yeah, they work pretty well actually.
Yeah, well, I think one of the upsides is Jacob has decided to wear his PJs, and nobody really knows except for now since I told you. So, um, but yeah, so welcome everybody. This is um, never boring. I'd like to welcome you to the doctoral defense by Jacob Misch. Just in terms of sort of the logistics of it, this is a public presentation, and so we're certainly happy to have you. And you're welcome to lurk or participate as much as you want, which is so much easier when you're remote, I guess. And we'll ask Jacob to tell a story about what he's spent his last few years on. And he's done a lot of work, and he'll cover it in as clear a way as he can. But if you have questions, feel free to ask them. You're certainly welcome to ask him questions, and he'll ask for questions. And then we're going to excuse the members of the public, as we'll say, and we'll squirrel away and do a couple academic sort of specific things that are sort of the nature of his degree in bioengineering, and cover some of the sort of the side details. I'm sure some of you will try to re-engage him sometime today or online. A lot different than when we're all in the same room, and but we're certainly glad everybody's here. Does anybody have any questions? Any of the committee members? We'll sort of squirrel away later. But...
So, quick question. This is my first participation in a PhD dissertation, so thanks for the opportunity. Now, will this be your graduation then, Jacob?
So he won't be walking across the stage in a cap and gown. We can guarantee that. So this is his final assessment, and so this assessment comes in a couple parts. It comes in way of his presentation, and it comes in way of his document. And so the committee members have been given rubrics to fill out relative to the defense, right? His presentation. And so you'll see that rubric.
Two of them. Two.
Yeah, there's two. One's for bioengineering and one's for mechanical engineering. And they're obviously, they have a relationship to each other, but they're fundamentally and structurally different. So we're going to ask the committees to fill those out. We also will talk a bit about revisions to the document. And that's one of the things we talk about when we squirrel away, just amongst ourselves and then with Jacob, because that's not really of interest or, for the public at large, right? It's kind of, they don't have the document, what do they care that he's going to be dealing with periods and commas and content, right? So that's what we'll do today. You'll be able to ask him questions either in the public time, or if you have more private questions that you want to ask that you don't want to do necessarily in public, that's fine too. And then I'll ask everybody about to disclose to us what revisions they would like to see in the document. Or sometimes some people send revisions directly to Jacob, but I tend to be a gatekeeper in terms of that to make it easy to facilitate between the committee and the candidate. Is that sort of clear? We have sort of two means of assessment here. But yeah, unless, but he's on track. He has to turn this in. What date do you have to turn this in by? December
4th or 6th. I can't remember the exact date, but it's coming up.
Yeah. So he has 3 weeks to get everything done that we ask him to do in order to get his degree conferred in December. Right? That's a good question. All right. If there's nothing else, I'm sitting in a phone booth here. We're ready to go. I'll turn it over to you, so you don't have to wait any longer.
Fantastic. Thank you, Dr. Spriggle. I've got a lot to cover here today. So I'm going to present in 2 parts, basically. The first part is going to be covering the test methods and testbed development, and then midway through the presentation, I'm going to stop and ask for some questions. I might have 5 minutes for questions, so 1, 2, maybe 3 questions there. Any other questions about any of the studies or any further follow-up questions about the test methods and the testbed? If you can, please save them to the end of the presentation when we have a bit more time to go through them. So without further ado, I'm very excited and happy to present to you today my work on mechanical performance characterization of manual wheelchairs. Before we get too far, I want to go over some numbers. So according to the US Census in the Disabilities Report data, in 2010, there were about 3.6 million wheelchair users in the US alone. And by 2014, that number had grown to 5.5 million. Now, regardless of why that number may have grown, we can assume by 2020 that number is at least 5.5 million. So many people daily use manual wheelchairs. And to give you some context of use, from some studies we've done here in the Rear Lab, the daily travel of at least full-time active users averages about 1.4 to 1.6 kilometers a day. Probably a little bit different in recent times now that it's a little harder to get out and about. But these bouts of mobility are fairly short. They're about 20 to 30 seconds. They have frequent starts, stops, and turns, and they're slow. They're about 0.4 to 0.6 meters per second. And to give some context to that, walking pace is typically described as above a comfortable walking pace is 1.0 to 1.4 meters per second. So just like automobiles, there are various ways to categorize wheelchairs, and the most predominant one given by the HCPCS, or Healthcare Common Procedure Coding System, is by using K-codes. So I've shown here the 5 categories for the most common sort of daily use wheelchairs. Starting from the K1, the standard or the depot chair. This is the kind you'd see at the airport or the hospital. It's for very quick transport from point A to point B, and it's typically pushed by an external caregiver. So they grip the handlebars and push the occupant around. And the same for the K2. The seat's a little lower, so the user can self-propel by walking along with their feet, basically. K3 is a lightweight chair. This is the first time that the weight of the frame is capped. Instead of pretty much any weight, it's now between 34 and 36 pounds. Moving ahead to the K4, the high-strength lightweight chair, the frame is lighter, and now it has I think it's a lifetime warranty. And a K5 being the high-tier wheelchair is the ultra-lightweight chair. This frame is capped at 30 pounds, so it could be 20, or it could be 29.9, anything below or equal to 30 pounds. And this category requires some customizability. So these are typically made to order to fit the user exactly with their measurements, their specifications. This includes switching out the wheels, the drive wheels, the casters, changing the axle position to accommodate for different weight distributions, pretty much anything you can think of. So just in summary, these K1 through 3 are predominantly short-term use, less than 3 months. It's for recovery or rehabilitation, so if you break your foot, for example, and it's for less than 2 hours a day, versus K4 and K5, which are full-time use and require self-propulsion using the occupant gripping the push rims on the wheels. As you can see from this table, however, there is no performance metric. There's no performance characterization in these 5K codes. And as you can probably guess from the title of this presentation, that's what we focus on. That's where we come in. A couple of ways that folks in the past have tried to rate different wheelchair performances or assess different design decisions are using human subjects. So you can look at the speed, distance, and usage similar to where we got the daily usage stats from and see how different categories are used, how often people use each chair, how fast they go, how far they go. Or you can look at the energetic metabolic cost of travel, so how much energy the human body expends to propel this wheelchair a certain distance. But with any study with human subjects, especially with wheelchair users, the population is sort of small. It's hard to get a lot of subjects for any study. And this metabolic cost assessment is exhaustive. It goes until fatigue, which is probably too much to ask for an already sort of vulnerable population. A more objective and mechanical way to rate performance, not necessarily of the wheelchair, but you can take the wheels off and put them on a mechanical test surface, a benchtop test, basically. So for example, this is our in-lab designed coast down cart to assess the rolling resistance and basic linear energy loss of drive wheels or casters. And you can see our publication here. And then the final way, which is probably a bit more clinically relevant and relevant to the manufacturers and to the users especially, is a system-based test. If there's a way to mechanically characterize the manual wheelchair performance, it's best done at the system level. So we've defined a metric that I'll refer to as propulsion cost, and you can think of it as very similar to gas mileage in automobiles. It is the amount of energy spent to move a certain distance mechanically. The test bed that we use for this metric is the AMPS, or Anatomical Model Propulsion System. And it's designed, it's this robot here sitting in a chair. The chair is attached to it temporarily, but it's not a part of the robotic design itself. So this robot is designed to resemble the average human male wheelchair operator. It can sit in virtually any manual wheelchair as long as it can fit within the wheels. So we can't use too narrow or even too wide of a wheelchair, but for the most common sizes, the amps can fit in every chair. And the way it works is that it's got these two arms that come down with, instead of a hand that'll move and push the push rims, it's got a motor. And we've got a gear on the end of that motor that meshes with a custom-made push rim that we attach to whatever wheels we're testing. So this is sort of a direct drive system. If we tell the motors to drive forward at a certain speed, the whole chair is propelled by that speed. I'll show you an example of that next. So to get to the metric of propulsion cost, we follow this series of calculations and data collection. So the way the amps worked when I picked up the project was that it was velocity controlled. So we would tell it to drive a certain velocity. In this case, if you follow the blue line, it starts from rest, accelerates to a target velocity, holds that velocity, and then decelerates. I'm going to play a video here. It may kind of stutter and buffer, but you should be able to see how the amps behave. So here is it driving at a steady state velocity. There's the deceleration, and then it comes to a stop. And so the amps hold motor torque, whatever torque it needed to achieve that motion. So we have two different sets of data here, the wheel velocity and the wheel torque. Now, to get to the energy that we supply to the system, we need to multiply these two terms together. So the torque of the wheel times the velocity of the wheel gives us a power curve. You can see the power that we supply to the system over time. And then to arrive at the total work, or the total energy in joules that we supply to the system, we can integrate this curve and find the area under the curve to get this line down here over time. So at the beginning, obviously, we supply no work to the system. It's at rest. And as we accelerate, as we hold steady state, as we decelerate, and then finally at the end of the maneuver, this is the cumulative number of joules that we've supplied to the system. To translate this into cost, we would then take that end data at the end of the maneuver, take that end work value, and divide by the total distance traveled by the center of mass. This gives us joules of energy per meter that the system traveled. Now, we've previously used this in a few different ways, but the most recent publication we got out of it was comparing the propulsion cost of any wheelchair system with the data that we collected of the components of that system. So if you remember a couple slides earlier, I talked about the coast-down cart, where we can measure the rolling resistance and energy loss of the drive wheels and casters. So we were trying to relate the system-level performance to the component-level performance. And what we found is that energy losses were the dominant predictor of propulsion cost. So we didn't need to know the mass of the system or even the weight distribution of the system, as long as we knew the energy losses at the wheels. And the main takeaway here is that mass was not identified as a significant predictor. And our hypothesis is that it's because that steady velocity is not reflective of how a human interacts with the chair. They use more of a push and coast, this cyclic motion that reaccelerates the mass with every single push, versus what the AMPS was doing is just accelerating it once. And so my main objective for my dissertation work in this presentation, to establish a test method with a reliable and repeatable robotic test bed, the AMPS, quantify mechanical performances of disparate manual wheelchairs in real-world use scenarios, with a particular interest in those factors that weren't listed as significant predictors of the system-level performance. So my first specific aim, again, is to develop, implement, and validate different augmentations to the AMPS that would allow for a new propulsion style that would permit this cyclic motion of the wheelchair. So I'll go over some human use data. I'll talk about some further updates to the AMPS that we've done and the validation of those updates. So let's talk about how humans use the chair. They follow, like I was talking about, this push and recovery cycle. So they grip the wheel, they push the wheel, apply a torque about the wheel or a tangential force to the push rim. And then once they reach a biomechanical limit, the end of their reach, basically, where they can't provide any more positive torque on the wheel, they release. And the wheelchair is free to coast on its own as the human is resetting their hands back to the contact point. Now, this is typically, human manual wheelchair use is typically measured in simulated environments, such as on a dynamometer or a large roller or a treadmill. There are few that record human use over ground using instrumented push rims, which is where I believe this data comes from. So if you look at just the wheel velocity of a human using a chair driving in more or less a straight line, you've got a very rapid acceleration of the system from rest to 0.5, and then in the second push up to 1.25, and then as the pushes go on and on and on, by the third, fourth, fifth push, the user has reached their chosen velocity, their travel or terminal velocity, if you will. With the previous iteration of the AMPS, it would have been difficult to maintain this motion because the AMPS would have tried to decelerate the system in between all of these pushes. But if you look at the torque that the human applied to the system, it seems a lot more repeatable. You've got maybe one inconsistency here where the first push is longer, wider, just a heavier push overall. And then every consecutive push after that has the same shape. The only difference might be, say, the peak magnitude of those pushes. So we thought if we could recreate this torque cycle using the amps, we'd have a better chance of mimicking how a human uses the chair. So again, the goal of this aspect of the dissertation work was to augment the amps, to apply the same exact input to every single chair it tests. You can think of this as creating what I like to refer to as the perfect test subject. Unlike human users, this robot has no fatigue. Right? It's got a charge cycle for the batteries. That's about it. It's repeatable, it's predictable, and most importantly, it has controllable behavior. And so, in this case, our chosen input to the wheelchair from the amps would be torque that it applies to the wheels through the motors. And we would be able to control the timing and the magnitude of those pushes. Now, to achieve that coasting motion I was talking about, we had to make some hardware changes to the system. We implemented a mechanical clutch for this intermittent coasting. I'm going to play a video here. Again, it might be stuttering a little bit, but I'll try to point out the main features. So pay close attention to this white gear and then this motor shaft here. Pay attention to this set screw in the motor shaft. So as the system starts moving, you've got little bursts of motion at the motor shaft, but the gear is in continuous, consistent motion. And what this is showing is that the wheel, as soon as it's going faster than the motor, decouples from the motor. So we're no longer back driving the motor, and the motor doesn't have to decelerate the system anymore. It has no power to decelerate the system. So we're seeing the wheelchair coast nearly freely. And using some just basic push and release coast down tests, we found that we reduced the deceleration of the motor attachment by nearly 80% just by adding these overrunning clutches. So with nothing connected, we had this deceleration. If we directly geared the system so as it was coasting down, it would backdrive the motors, we had this acceleration. By adding the clutch, we reduced that added deceleration by 80%. Next, the software changes that we made. I want to go over the general flow. The details behind it are probably enough for its own presentation, so I wanted to talk through the general gist of it first. So the idea is that we'd create a desired torque profile before any trials are run. We'd generate a maneuver, and then we'd send it into the system, into the motor controller. And we want to get a desired torque. This motor controller has to interpret how to get that desired torque from the motors. This is the block diagram that we used. It fundamentally relies on the fact that torque and motor current are proportional. And so this motor controller is doing all of the heavy lifting for us. It's taking a desired torque, figuring out what voltage it needs to apply across the motor terminals to reach this, this torque output. Again, the controller output is in voltage, and it's defined by this series of equations derived from Kirchhoff's current and voltage laws. And if you were present at the proposal, you might remember me talking about this runaway response we were having. So the system was basically chasing its tail. If we would set a desired torque that was too high, as soon as the system would start to attain motion and start to accelerate, the attainable torque would decrease. And so our only option was to keep raising voltage, raising velocity of the system, making that torque harder and harder to get to. So to combat this, we added a feedback loop from the encoder or the speed sensor that would prevent this, this runaway response. It would limit the speed and prevent the thing from just sprinting down the hallway if I hit the wrong button. And then again, the output is still voltage. So we don't have to change any more hardware of the system. To validate this torque control, this torque controller performance, we set the amps up in a stationary torque testing rig. Let me blow up the detailed view here. We've put a force gauge in line with the wheel. This is just a tension force gauge. And it's got a hook at the end of the force gauge transducer. And along that hook is a steel cable. The steel cable comes out, wraps around a pulley, comes up, and hooks onto one of the push rim standoffs. So basically, we've got we're measuring the tangential force that we apply to the wheel. On the other end of the wheel, we're pre-tensioning the system with a spring that's attached to our test rig's base. And we would send in command currents of 5 amps, 7.5 amps, 10 amps, and 15 amps. And again, torque and current are proportional. So these represent a very specific torque in Newton meters. So in this case, we send in a command of 10 amps, which should be approximately 5.5 Newton meters. And we hold this command for 5 seconds and then let the system go back down to a stop. And out of 5 trials, you can see the current signal, or the torque, is a little bouncy. It jumps around the signal, the target voltage, the target torque quite a bit, but for the most part, it stays right on that line. And we found that the standard error of the mean was very consistently under 0.05 Newton meters. And this is a 5.5 Newton meter target, so 0.05 Newton meters is, practically speaking, nothing. And then for our validation, we found that there was some variability in the force gauge itself, but we were within 10% from the torques measured by the force gauge setup over the 5 trials at each of these commanded torques over each arm. So very stellar performance from this. We then wanted to tune the commands that we would send to the motor controller, because with any system, with any electromechanical system that involves a motor, it takes some time to ramp up. There's some inertia behind the system. And so we varied the shape and size and magnitude and duration of the commands that we would send into the motor controller. You can see here a triangle, a rectangle, and we start getting more trapezoidal at this 0.6, 0.7, 0.8, 0.9. So these just represent different ways that we can just blip a desired torque to the motor controller and have it sort of try to reach this output. And we found that overall, out of this set of trials, the 0.6 second command, the 0.6 second total duration command output had the lowest deviation from our command. The actual output deviated the lowest from the command. This was later tuned to about 0.55 seconds. So you'll see that later on when I talk about the maneuvers. For example, right here. To generate different maneuvers, we leaned heavily on the literature and figuring out how humans use the chair to travel in different trajectories. And the most readily available ones were in straight motion. So we can clearly see how a human uses the chair to push from a stop up to a steady speed and maintain that steady speed before coming to a stop. This is mimicking that in a very parametric way that we can fine-tune as needed. So the torque about the wheel against the time. The first push is a very heavy, higher magnitude, longer push, just like you saw in that picture from Critchlow's dissertation. And as we get closer and closer to reaching that terminal or travel velocity, the torques get less and less because you just don't need that much power behind each push to maintain velocity. You do need it to accelerate the system. And so here's a video of the straight maneuver at work. The main takeaway from this is that we are endowing the system with motion in a straightforward direction, which translates the mass straight forward, and the wheels are experiencing rolling, pure rolling, and so we can, this represents like rolling resistance, the energy losses of just pure straight motion of the wheelchair system. To capture pretty much all of the other parts of motion, for example, if you're turning, you're scrubbing one wheel against the floor, or you're swiveling your caster at the front of the chair, or you're just exerting energy to change your heading direction. There's some energy expenditure there just by changing the way the chair is facing. We generated this slalom maneuver. It's got sort of this serpentine motion you can see here in this plot. And the main features of the torque trajectory are the first push, a bilateral both-arm push to align the casters. So let me play the video. Watch this first push here. It goes straight forward to make sure the casters are both lined straight, and then it alternates left, right, to give the system this serpentine-like motion. So again, this emulates the cornering forces, the side loading, the scrubbing of the drive wheels in the casters, and the swiveling of the casters for a wide range of different sources of energy loss. So now to validate the system in an overground trial, we took a look at what a command was into the motor controller versus what the actual torque output was. And it's really hard to see in this plot just because they're so closely aligned, but the solid lines here are the actual output of the system, the torques produced by the motors, and the dashed lines are the commands we sent in. The biggest deviations occur when we drop the torques back down to zero. The motors really don't know how to behave when they try to hit zero torque and they've got no resistance because of the clutch. So they kind of overshoot typically when they hit that bottom, that zero command. But the main point of this is that if you look at the root mean square deviation of just the torque across both wheels, we have an RMSD of less than 0.3 Newton meters. Again, we're looking at torques of at least 5 Newton meters up to about 20 Newton meters. So 0.3 Newton meters of deviation really doesn't change the output of the system too much. If you normalize that, at least for this trial, by the peak torque to get the normalized root mean square deviation, you see it's only about 2% deviation. And then if you take the mean absolute error across the entire maneuver, that value drops down to less than 0.15 Newton meters. So very consistent torque outputs. We have a lot of faith in our ability to provide these repeatable torque pushes to any chair that we test. So in summary of the amps, I wanted to go through some of the subsystems just so you understand the basic layout of it. We've got our main high-level controller up here. This is where the user interacts with the system. This is where I generate the torque profiles and monitor the signals that are coming in. This communicates with both the data acquisition system down here in the abdomen and the Robotech motor controller that actually goes out, sends the commands directly to the motors themselves. We measure torque output, or we estimate torque output, I should say, using these current sensors that are mounted on the biceps. Since we know that current and torque are proportional, and we've determined that proportionality constant, we can measure the current flowing through each motor to estimate the torque output on each wheel. The other signal that we measure comes from the drive wheel encoder on either side. This tells us the instantaneous position of the wheel, and then as the system moves, we can track those differences in position to figure out the velocity of the wheel and the velocity of the overall system. So in summary of this section, I've showed you the validation of the current-based torque control of the motors in both stationary and in overground motion. I've shown you our generated maneuvers that emulate different parts of wheelchair motion in both rectilinear or straight motion and curvilinear or slalom serpentine motion. And this system maintains that same output metric, that propulsion cost that I went through earlier. And this augmented amps is specifically designed to mechanically and objectively measure the performance or propulsion cost of various wheelchairs across many different design choices. I want to take just a brief period of time and go through our outcome variables. We identified 4 for all of the studies. Again, the torque is what we hold constant. This is what you saw when I generated the maneuvers. This is what we're sending into the wheelchair from the amps. So for this torque profile, for this particular test, the chair exhibited this motion, this velocity. So the first outcome variable is distance. And this is represented by sort of just the area under this curve. Velocity is in meters per second. We multiply that by the seconds of the maneuver to find the total distance that it traveled. Right? Just integrate along this line. Propulsion cost, as I went over earlier, is found by multiplying our wheel torque and our wheel velocities to get power, and then integrating that in the same method over time to get the representative work plot, or the total amount of energy that we supply, the cumulative amount of energy that we supply to the system throughout the whole maneuver. We then divide that end work value by the total distance traveled by the center of mass. The third is the max attainable kinetic energy. This represents sort of just a combination of all of the motion in the system. The motion being the output of the wheelchair, the input being the pushes, the torques from the motors. So we were using this as a way to relate the output, the energetic output of the system to the input. And we use a series of equations that I'm not going to show here, but in general, we take a look at the rolling of the drive wheels and the casters, as well as the swiveling motion of the casters and the entire wheelchair itself as it turns about its center of mass. And we include, of course, the translation, the linear translation of the mass of the system in this kinetic energy equation. And finally, the last one is very specific to just the slalom or the turning maneuver, is the yaw displacement. And you can think of this as just, I'm sitting in a nice rolly chair right now. So as I turn, my heading direction changes. That's an angular yaw displacement about my vertical axis. So rather than presenting all four of these metrics, however, we wanted to kind of summarize everything and make it as concise as possible. So I ran just an investigation on the correlation coefficients between all of these metrics and found that distance and kinetic energy are both fairly highly correlated with cost, whereas yaw showed less of a correlation with cost, but it was fairly highly correlated with both kinetic energy and the distance in the slalom maneuver. So what this suggests to me is that showing all four of these might be showing the same trends over and over and over. And for concision's sake, we chose to just present one metric, the propulsion cost, as the representation of the mechanical performance of the wheelchair system. And then the general data flow, after we run a trial, after we propel one chair down the hallway, we would run a Butterworth filter just to clean up some of the jaggedness of the sensor signals on both the wheel torques and the wheel velocities. We would then use these signals to calculate all four of our outcome variables, the cost, the distance, the yaw, the kinetic energy. And then we would have basically one value for each of these for each trial that we run. To test for normality of the data distribution, we use the Kolmogorov-Smirnov test. If normality is not found, we use a Box-Cox transformation to normalize the data to be able to run analyses that require normal distributions of data. But for the sake of this presentation, I'm going to go over the basic descriptive stats, so the mean, the standard deviation, the percent difference. I'll show you effect size so you get an idea of the magnitude of difference between the groups, and equivalence testing to figure out if two groups have equivalent performance. A little bit more detail about equivalence testing, say you had two data sets of the same variable. So I have cost for a test set of chairs, or sorry, a single test chair and a control chair. What this chart is plotting is the 95% confidence interval of the difference between these two group propulsion costs in this example. You can think of this sort of like a t-test, except instead of testing that the difference is 0, we're testing that the difference is comfortably within a bounded envelope, denoted by this epsilon value. So in this particular case, and in all the studies I'll be going through next, the epsilon was chosen as plus or minus 5% of the control mean. This is a practically relevant bounds. So say in pharmacology, this would be, say, 20%. We're looking for 20%, less than 20% differences between two different drugs, for example. And we refer to this blue box. You'll see this in all the slides that I go through. This is the equivalence interval. So if I go through these two cases, case one, the difference is centered almost at 0. And you can see this 95% confidence interval is firmly within these bounds. We can say that these two groups, at least in case one, have equivalent performance. Case two, however, has no bounds, or the confidence interval is completely outside of bounds. We would say that these are not equivalent, and in fact, one is superior or inferior to the other one. Right? In this case, yeah. We can also use this same test method in a one-sided way. Instead of bounding both sides, we can set one of these limits to negative or positive infinity, and just see if the lower bound, let's take case two, see if the lower bound of this confidence interval is completely outside of this blue shaded box. And if so, we can say that it is inferior or superior, as the case may be. With all that being said, I'd like to open it up to questions. The rest of the entire presentation relies on understanding of the test bed and the test methods, as well as the analysis that I've talked about so far. So I'd like to turn it over to the audience if you have any questions for about 5 minutes. Yep.
So Jacob, you talked about the torque peaks that were applied.
Mm-hmm.
And I saw that the torque peaks were kind of diminishing as you went through the acceleration phase, right?
Mm-hmm.
Why did you pick those torque profiles? Was there a correlation to the actual user strokes?
Yes. So I guess if I go back to that slide with Critchlow's data, you're right. It doesn't. Let's see. Can you see that?
Yeah.
So this is probably a pretty bad example to use to compare to what our generated torques are. Our pre-generated torque profiles are actually more realistic, more comparable to the average human use of the wheelchair. Again, you have to remember the context of use of these chairs. They're slow. In this particular image, the user was going up to about 2 meters per second, much faster than we intended to go with the amps with our system. And so the torque peaks in this plot stayed consistently high to keep that momentum, to reaccelerate that system to that high speed. Does that make sense?
Yeah, if you go forward a couple more slides, one more. Okay, stay right there. Actually, go one more.
To the slalom?
No, I want to see the actual torque profiles that you programmed in. Oh, there, right there. Oh,
this one. Okay.
Right. So you see the peaks are diminishing, right, as you go, as you step through the different time steps. So my question is, what is driving those peaks? How did you get to those peaks?
This was sort of there was an extensive literature search first to see if we can just look at the data and figure out, has someone measured the motion we're looking for? This sort of a gradual ramp up to about 0.75 meters per second, give or take. And we couldn't really find this. We found that people recorded pretty much as fast as they could, right? They told the subject to sit in the chair, go as fast as you could. And so you'll see a lot of data that goes up to 2 meters per second, 2.5 meters per second. Not very representative of what we were trying to do. And there's very limited data for this slower propulsion. And so this was made with a little bit of information from the literature for at least the first 2 or 3 peaks. And then this was trial and error. We were trying to find what torque peaks were going to give us a steady travel velocity. So we had a chair that we started with, just an ultra lightweight chair that we put the amps on, and we were trying to tune this command. We spent about 3 months tuning this command to get a nice gradual ramp up to about anywhere from 0.75 to 1 meter per second, and hold it there for these 4 strokes. Does that answer your question?
Yeah, it does. So basically, if you're looking at the travel of your wheelchair from start to finish, it takes approximately 13 seconds, let's say, right, for that travel. And these are the strokes from the robot onto the wheels, correct?
I think this one might show it a little bit better. Yeah, so the torque that we supply to the wheelchair ends in 12, 13 seconds. And then the system obviously needs some time to coast down. So we have this nice gradual deceleration period where it returns to a stop.
Okay.
So the full maneuver is more like 20, 25 seconds. But the torques that we apply last about 12, 13, if that clears it up a little bit.
Okay. Yeah, thanks. That explains it.
Are there any other questions for this? I can't actually, I don't have the presenter or the participant view. So
There are no questions in the chat. I
Okay.
can report that.
Fantastic.
Yeah.
All right, let me
I
get
don't
back
see
to.
anybody raising their hand either.
Oh, you're such a teacher.
Yeah.
All right. If you do have any more questions after this point, we'll have another question section at the very end of the presentation. But without further ado, I want to jump right into the 3 studies. So again, in just a quick summary of the previous section, we've validated the amps in its use in 2 different types of motion, straight and slalom, for stationary and overground torque outputs, basically. And so now the goals of the rest of this presentation are to use this amps test bed and that same propulsion cost output, that same statistical analysis to assess differences between different manual wheelchair design choices. The 3 that we selected were frame mass components, such the drive wheels and the casters of the system, and the frame type, whether it's folding or a rigid chair. The first study, specific aim 2, was to investigate the effect of incremental changes in frame mass. I'll look at some of the preliminary human study results, talk about some minor modifications to the amps, and then go through the objective mechanical results, being propulsion cost in this case. So to walk you through my logic a little bit, we have to ask ourselves, why would frame mass matter? According to the HCPCS coding policy, there are only 6 pounds of frame weight, 30 to 36 pounds, separating the standard, the lowest tier, the depot chair, and the ultra lightweight, this full-time use, very high quality manual wheelchair. And so what is the justification of that frame weight separation? And if you go back to just a basic free body diagram, the force and the mass are proportional to each other, holding acceleration constant. So an increase in mass would require an increase in force to achieve the same acceleration. This is just a fundamental principle of physics. But in more context, you can think of it as loading into and out of vehicles. So if you have to constantly, every day, multiple times a day, lift and load this thing into a car, mass or weight might become a little bit more important. And there's also the aspect that with the push and recovery cycle, the propulsion cycle of a human user, there's a constant reacceleration of the system with every single push. So if you have a higher mass and you're trying to get that same acceleration, you're putting more forces, more torques on the wheel, you're putting more load on your shoulders and your upper body. But put this into perspective and to give you a little bit of context here, we're talking about, say, a 1 kg or a 2 kg addition to the system, right? So if you just look at a 10 kg frame and add 1 kg to it, that's about a 10% increase in your total system mass, right? That seems fairly significant. However, once you sit in the system, assume you're a 90 kg wheelchair user sitting on a 10 kg frame, that 1 kg shrinks to only 1% change in your overall system mass. So it should be fairly expected that humans have shown insensitivity to changes in the frame mass. There are a few studies I want to go through using frame mass as an isolated variable. What I mean by this is they took a single chair and a number of human users, and they just added mass at the center of mass location to increase the mass of the chair in a very subtle way, 1 kg, 2, and 5 kg. Some studies went a little bit more aggressive and added 5 kg and 10 kg to the chair. And what these studies reported is that there were no changes in cardiorespiratory function in Sagawa's study, with up to 5 kg added to the frame itself. In the Groot and Bednarzic's studies, again, 5 kg and 10 kg added to the chair, de Groot reported that it had less of an effect on their outcome, which I believe was metabolic cost and pushroom forces, than just changing from a solid drive wheel tire to a pneumatic tire. And then Bednarzik reported no impact on the propulsion efforts. For a number of other studies have used mass as a sort of a system, they change the system and report the change in mass. So what I mean by this is that they use 2 different chairs. They use a light chair and a heavy chair without standardizing the 2 chairs. So there's no guarantee that the wheels or the bearings or the weight distribution or even the wheelbase of these 2 chairs are the same. So it might be conflating multiple aspects of the system. But they reported a 6% increase in pushroom forces. This is Cowan's study. And then Hilbers and White reported a 17% reduction, improvement in the metabolic cost by switching to a, 17% reduction with the lighter chair. But this was comparing a standard to an ultra lightweight chair. So there's way more going on behind the scenes than just changing mass. So what we can do with the amps is standardize a few of these features. So our experimental design produced 5 different loading configurations. We measured the mass and the weight distribution with this inertial measurement device, and so we can find out exactly where that center of mass is located. We added a shelf to the underside of an ultra lightweight wheelchair, and we just had the standard 80 kg amps sitting on this ultra lightweight wheelchair. Without any added weights to the system, we named this the 0A configuration. We had a weight distribution of about 72% of the total system weight over the drive wheels. We could add stacks of 2 or 4 kg to this platform, the center of mass, and without changing the weight distribution, we just changed the frame mass. Taking those same weights off of this shelf and moving them to the footrest, however, you can see did have an effect on the weight distribution. So it's assessing 2 different things: the effect of mass alone and the effect of that mass placement. An overview of this study here. I'm not going to make you go through all of these details, but we controlled the components. We used 1 single set of drive wheels, 1 single set of casters. We controlled the occupants, so of course, the 80 kg amps, controlled the weight distribution by figuring out what that center of mass was for the 0A, 2A, and 4A configurations, and then measured the weight distribution for the 2F and 4F configurations. And all said and done with the 2 maneuvers, the straight and slalom, with a total of 30 trials, 30 overground trials per chair, equaled a total number of 300 amps, overground amps trials for this study. So I'll play another video of the straight maneuver here just to reiterate how the test looks, how each trial looks. From this particular trial, we can get the torques and the distances, we can figure out propulsion cost, and the three other outcome variables that I'm not going to talk about today. These are the same maneuvers that you saw in the previous section that we deploy for this study. So digging into some of the results here, this is what the straight maneuver outcome looked like. This is propulsion cost plotted on these axes here. You can see cost in joules per meter on this axis, and then you've got the different groupings. This is the 0A or the default configuration. This is the 2A and the 4A in blue, and then the 2F and 4F in red. And I have to point out this y-axis is very small relatively. This is 1.2 joules per meter. And so we're not looking at great changes in between any of these groupings. You can see reflected down here, the OA configuration had a cost on average of 8.89 joules per meter. As you move up, as you add more mass to the system, that cost increases, with the worst coming in at 9.43 for a whopping change of about 6% increase in cost by taking all of those masses and stacking them on the footrest. This is the equivalent of adding roughly 10 pounds directly to the footrest, right above the casters. And there are large effect sizes as you get further up in the masses, indicating that they are further and further separated. Looking at the non-inferiority testing, we're using a one-sided equivalence test or a non-inferiority test here. And so our envelope, our threshold, is from this 5% threshold all the way down to negative infinity. And I need to point out, decreased cost here is better. So a 0 or below would indicate equivalent or better performances, whereas anything to the right of this is indicating progressively worse performances. And you can say, you can see that the 2A, 4A, 2F, and 4F, they all had one tail of this confidence interval of the differences within this envelope. So we can't say definitively that any of these loading configurations were statistically inferior by over 5%. We can't say they're equivalent either, but we can't say they're inferior. They're just in that sort of middle grounds. Moving directly on to the slalom maneuver, you can see that our costs are once again plotted 0A, 2A, 4A, 2F, and 4F. You've got a slightly stranger trend where now the footrest loading is a little bit below, if anything, the default configuration. However, this axis, the y-axis here, covers only 0.5 joules per meter. So any changes that you see in this plot are just minuscule. And you can see that reflected by our percent change values down here. Everything is less than a 1.5% change in the cost. So it should come without surprise that all of our differences in our inferiority testing are centered pretty much right around 0. Very, very close to the unity or 0 line. And so as I plot this equivalence envelope, all of these are within it. We can say that these are equivalent performances. Every single loading configuration had equivalent performance, give or take, the 5% threshold. So to discuss some of these points, I can say that mass does have a very slight influence on the mechanical performance of the wheelchair. It's slight, but it is noticeable only at the robotic level. So you get a 4% cost difference, a cost decrement by placing the 2 or 4 kg masses on the system, but it really depends on where you place them if you can optimize this system. Right? So if you have all of this weight centered over the casters, it worsens the effect. So now it goes from 4 to 6%. And a little fun fact about this study, is that the plus 4 kg on the axle, right, this nearly 10-pound stack of weights on the axle or at the center of mass had roughly the same effect as only half that stack on the footrest, indicating that the placement is probably the more important factor out of this study. And I would also like to point out that if any of these configurations, especially in the slalom where you saw all of the costs were functionally equivalent at the robotic level, it's almost impossible that a human user would ever notice a difference between these configurations in that same style of motion. So, in summary of this study, our data more or less supported most findings from the human trials in that there's really not much of a noticeable difference just from frame mass. There is a slight impact that we can detect with the amps, but it's almost definitely not enough for a human user to feel. We can't claim that any of these configurations had statistically inferior mechanical performance. Moving on to the second study, this one looked at components that you can place on a wheelchair, the drive wheels and the casters. And I'm focused on the K4, or the high-strength lightweight chair, in contrast to the K5, the higher-tier chair that we used in the previous study. We chose this because it traditionally has a lack of configuration options. It's sort of a you get what you get sort of wheelchair. Again, I'll go through the experimental design and then talk through the results that we got, the propulsion cost results. So, as a little bit of background for this study, I'd like to talk through why we chose the high-strength lightweight chair. According to the HCPCS coding policies, the K4 is the first category that requires self-propulsion. So you're not relying on someone standing behind you with the handlebars pushing you around. You have to be able to move this thing under your own ability. And it has limited configuration options. So unlike the K5, where you can completely custom fit it to yourself, this has typically one set of components that you get. It's got one locked-in weight distribution unless you physically shift forward or backward in your seat. And you can't change the axle position. So for this study, we chose a representative K4 chair. This is the one we picked, pictured here. So our goal was to improve, see how far we could take this chair on a budget. So keep in mind the context of use. All of these sort of more full-time use wheelchairs are used indoor and out, but the predominant use is indoors on a carpet or tile, most likely a tile surface. And they also favor low-maintenance components. What I mean by this is that you want a solid drive wheel, just a solid urethane drive wheel versus a pneumatic wheel that you might have to check inflation every other week or every month. So keeping all of this in mind, we have an additional restriction of budget. So these K4 chairs cost on average roughly $600. You can find them for as low as $150, $200, and they can go upwards of $1,000 if you look in certain places, versus a change in wheels and tires where the prices start much lower, so $15 in some cases. So our goal was to make improvements to this default representative K4 frame with a limited less than $100 budget. Our experimental design consisted of 4 different configurations with labeled by letter. So the A configuration here is just the default. It has a solid mag tire and an unbranded, just off-the-shelf 8 by 1 inch caster. The first changed configuration, configuration B, we swapped out the 8 by 1 inch caster for an upcharged variant. It costs about $50 per pair, the Primo 6 by 1.5 inch caster. The third configuration, configuration C, put back on the 8 inch caster, the default caster, and instead swapped out the drive wheels for another common solid drive wheel, the Primo Express. Again, a pair of these is about $50. And then for the fourth configuration, we swapped out both of them. So the entire thing had upcharged components for a grand total of about $100 change. And I want to point out, don't want to spend much time on it, but these were chosen based on their performances in the component level tests. So the scrub torque test rig and that coast down cart that I showed you in the intro, where we measured the rolling resistance and other energy losses of these wheels. So we chose these particular wheels specifically. So again, going through the overview of the study, 4 different configurations, 2 different maneuvers. You've got your straight and your slalom maneuver. And in this test, we chose 2 different surfaces, low pile carpet and a tile surface, for a grand total of 480 overgrounding. Here's a picture of the tiled surface that we used for the tile testing, and the carpeted surface that we used. And I wanted to show you just one video of the slalom maneuver. You can see in between these pushes, the chair coasts mostly to a stop in between pushes. So we had to increase the torques for both the straight and the slalom to just get continuous motion out of this system. So I don't want to spend much time on these at all, but I want to just gloss through the main takeaways from these slides. For the straight tile, you've got your default configuration up here with the by far highest cost. And then your swapped casters and your swapped drive wheels are significantly better. And then if you swap both of these, you get up to a 41% improvement in the mechanical performance, a decrease in the propulsion cost. It's no surprise that the equivalence test showed that all of these were outside of equivalence, definitely had lower cost values. For slalom, you see the same exact trends, just a little bit tighter groupings and less of a percent change. So this y-axis is much more tightly grouped. And again, you see that none of these fall within the equivalence threshold, so we can clearly see that these have a reduced cost. For the straight carpet, there's a much more linear trend. The casters didn't improve quite as well as the drive wheels did on carpet in straightforward motion, but swapping both of the components out did have a cumulative improvement for a grand total of about 18%. This one you see that the swapping out just the casters did not get out of that equivalence bounds. So we cannot say that these differed by more than 5%. And then the slalom carpet had, again, a very strange trend. So the casters actually worsened. The upcharged casters worsened the performance, but only by about 3%. And the other 2 reduced by about 6%. All of these are within the equivalence window. We can't say any of these differed by more than 5%. So in a brief discussion, components definitely matter. We got up to a 41% decrease in propulsion cost on tile, just by swapping out the casters themselves, changing nothing else of the system. There are a few discussions to be had here where larger casters, like the default casters, might be better at clearing obstacles. You're definitely not going to go up a curb on a 3-inch caster, but you might have a shot at it with an 8-inch caster. And also, not all forks fit all casters, so these changes that we saw here might not be possible on every single chair. So for the recommendations, just from this study alone, obviously switch the drive wheels and the casters. It had the best performance out of all of our test environments. If you only had one choice, though, the drive wheels really took the edge on the carpet, where the casters actually hurt performance. And then an additional caveat here, performances could be further improved based on our component level testing by swapping on pneumatic components. They tend to perform better than their solid variants. So this 41% could be completely blown out of the water by a pneumatic swap. So out of 480 amps trials, we've sort of proven that knowing this component performance can really streamline our process and let us choose a high-performing setup before we even get into the chair. Finally, the third study is looking at folding and rigid ultra lightweight frames and seeing if there's a performance trade-off between these two. So why did we choose frame type? It's the first major choice in wheelchair selection. So K5s have about a 5 to 10 page order form. But before you even get to the order form, you have to decide whether you want to look into a folding or rigid wheelchair. The main differences between them are portability. So one has a solid axle. It may have a folding back or something, but for the most part, the frame stays as one rigid unit versus the folding, which can collapse into a sort of a vertical column and reduce its footprint, which for some people may be easier to stow. But in recent years, since both have removable wheels and the rigid frames can fold down, that's become less of a spot of contention between the two. And there's also potentially a durability trade-off between the two, with folding actually taking the edge over rigid frames. So our question is there a performance difference between these two styles of frame? The way we designed this experiment was by choosing 6 different frames, 3 of each group. So we have the F1, F2, F3 for the foldings, and R1 through R3 for the rigid frames. These are representative of very common ultra lightweight chairs that are on the market currently. To spare you that big, long, extensive table, I've just summarized sort of the main features of this study. Again, 1 occupant mass, 1 weight distribution, 1 set of drive wheels and casters, 2 frame types. We have 6 total chairs. The system mass did change slightly between the chairs, but as we saw in study 1, we're not too concerned about that system level mass change. And the weight distribution was kept as close to 70 as we can get. I think we spent more time fiddling with this than collecting data, for a total of 180 total overground AMPS trials. The results are a lot more straightforward and simple this time. You've got your folding and you've got your rigid group. The folding had a slightly higher cost by about 0.3 joules per meter. Now, if you flash back to the second study, we had differences of 5 or even 10 joules per meter. So this 0.3 is functionally nothing, the 3% change. The equivalence, we see just one little tiny bit of the 95% confidence interval sticking out of our equivalence bounds, so we can't comfortably say they're equivalent, but it's really not far outside that plus 5% change. For the slalom, we see a similar trend. Rigid chairs still have a slight performance lead by about 0.12 joules per meter, so again, really nothing to speak of. It's a 1.2% change, and then this one is firmly within that equivalence window. So in the discussion, I'd like to just say it's not quite, maybe not quite as simple as just grouping by rigid and folding. You can see we had pretty disparate performances within groups. So you have 2 folding chairs that have very high cost versus one that has a slightly lower cost. In the rigid group, you had 2 that had the lower cost and 1 that had the higher cost. So there's a question about this study of, what if we had just chosen 2 chairs of each, right? If we had these 2 and these 2, we would have had much different findings. But again, in context, this is a grand total of maybe a 1 joule per meter change versus the 5 or 10 joules per meter from the previous study. So nothing really to speak of. From my professional standpoint, professional opinion on this, I would say that they're nearly functionally equivalent. We would need further testing that we're not currently equipped to do to investigate differences at a chair level instead of this folding versus rigid. In the grand summary of the entire dissertation, I've walked you through my 4 different aims: the augmentation of the AMPS and the validation, the investigation of incremental frame mass changes, the component tests, and the folding versus rigid tests. This new test method really does help us get a better understanding, just some mechanical insight into the mechanical wheelchair design, and objectively rate if a wheelchair design has a performance trade-off versus just being preference-based, like folding versus rigid. And it serves as a framework for countless future studies. And I have to end every slideshow by saying, sincerely hope that these results can help us identify some of these performance trade-offs, and that'll help clinicians and manufacturers prescribe better chairs, and the user might have a better chance at making an informed decision when they're choosing their own chair. A few future directions, just stuff that I will be changing in the coming months. We've got a proposed change to the amps, switching over to, again, a velocity-based intermittent propulsion. One of the main challenges we had with torque control is that we needed to tweak the torque values to make sure that every chair had motion or had constrained motion, so it didn't just fly down the hallway. If we had a velocity control, we would have a lot better handle on how fast each chair is going, and it should still maintain that same push coast. We're not taking off the clutch, so we're still going to get that coasting functionality. And then there are, again, countless possibilities for future studies. We've proposed a few that include energy dissipating components like casters or drive wheels, as well as suspension systems on frames. We've talked about simulated use, so we can test a wheelchair sort of out of the box versus out of 6 months or a year of simulated use. And we can also add potential energy to the system to really isolate that variable of mass as we're trying to go up a ramp, for example. Here are my journal publications. I've got 2 peer-reviewed journal articles. I've got 4 in preparation, the 4 different specific aims from my dissertation. I've been to a number of conferences through the years here at rearlab. And finally, I'd like to get to my acknowledgement slide. I'd like to thank my committee, especially Dr. Spriggle, who's helped me the entire way through my nearly 5 years here, all the past and present members of rearlab who have helped me with data collection or designing these test rigs, as well as my family and friends who've supported me along the way. My references that I've used throughout this presentation, and with that, I'd like to open it back up to questions.
All right, well, thanks. Somebody open their mic?
I have a question.
I was just clapping.
Oh, okay.
So Jacob, excellent presentation. I do have one question. So when you look at the propulsion costs, I think you said you were integrating the area under the curve to come up with the total energy, right? So were you integrating the entire curve under the total motion, or only up to the point where you were imparting the torque to it, the torque signals?
Let me go kind of a slog back there, but the picture is really going to help with this one, the diagram. So we integrate basically only where torque is applied, and the picture is more demonstrative. You can see that?
Yeah.
So after a certain point, since we stop applying any torque to the wheelchair, we're multiplying our velocity times our torque. So if the torque is 0, this torque times velocity becomes 0. And so we don't add any more energy to the system. So functionally, yes, we stop counting energy as soon as the final push is applied to the wheelchair, if that makes sense.
Yeah. So when you do that, a part of the energy is also coming from your coasting, right? Even though you're applying torque, there is a momentum that is already there, which is contributing to that area under that curve. Now, if you have a heavier chair, you have a higher momentum, which is going to give you that much extra boost in your energy. So how do you account for that momentum, for the inertia-based part of it that you're getting from the chair, extra weight?
That's actually an excellent question, and we spent a lot of time just agonizing over how to account for that. And the best way we could do that is because kinetic energy and distance had a very high correlation between the two of them. We just we decided to let the entire system post down after that final push. So even though we stopped counting work here, we don't stop counting distance. We count distance all the way to the bitter end where it finally comes to a complete stop. And so all of that kinetic energy, all of that momentum is spent by the system, and all of that energy is dissipated at the interface between the wheels and the ground. So this propulsion cost, because we use this end value of work and end value of distance, does account for all of that energy.
Yeah. So are you getting a boost from the heavier chair though? That's the question, right? Because the heavier chair has more inertia, so that'll give you a longer coasting distance, won't it?
You would think so, but I don't think the, I'd have to flash back to the dissertation document. I don't have the distance values tabulated in the slides here, but I believe actually the lighter chairs, because they were able to hit a higher velocity, they actually ended up coasting farther. So the distance and the cost were both better in the lighter chairs. Again, very, very slightly. You know, we're not talking differences that are, 10, 15, 20%. We're talking maybe 1 or 2% difference. If that, does that answer your question?
Yeah, it does. Thank you. Again, excellent presentation, very informative. Thank you.
Appreciate that.
So, Jake.
Yep.
Do you see test beds like this, or even potentially AMPS itself, being used to kind of adjust or reevaluate some of the HIC-PIC coatings in the future?
That's a big task, and that wasn't what we set out to do, right? We're just trying to investigate these differences so that we understand the performance trade-offs between these design decisions. Now, it certainly could be used, right? We assessed frame mass, and we saw that functionally, the mechanical performance didn't differ by enough to really segment all of these chairs into 5 distinct categories, right? So, but I think a lot more work would have to go into it to overturn the HIC-PICS codes, and that's certainly not what we're trying for.
Oh, yeah. No, I was thinking more just like in addition to it, like another category that goes under each of them. So, be like, here's performance cost based on a system like this.
But I think the better way to approach that is by saying, if I go to study 2, where we looked at the different components and saw how much of a performance boost or decrement choosing, the right or wrong wheels would have, we could easily just amend some of these policies to say, anything over a K1 needs to have a choice of components. You need to give the user a pneumatic and a solid tire option, for example, so they can make that choice themselves, and make that knowledge known to them that pneumatics tend to maybe have a little bit of a boost over solid tires. Does that make sense? That would be a much easier amendment or improvement to the HIC-PICS coding policies or other similar coding policies around the world, really, just to help the user more than anything.
So to follow up on the discussion before about your dependent measures, I was staring at them before when you expressed some surprise about the correlation between the measures, because mathematically your distance and your propulsion cost are nearly identical, right? They stay on the slide you were on.
This one?
Yeah. So mathematically your distance and your propulsion cost are nearly identical except for the coast down, right? Because it's a function of velocity. Your distance comes from your velocity, and your work comes from your velocity and your torque, where your torque is controlled across all conditions, so your torque doesn't vary. So really, it looks to me, if I'm understanding correctly, the biggest difference between your distance and your propulsion cost is that period of coast down. So I guess my question is, first, is that assumption, obviously not the same units of measure, but if that assumption is correct, how do these results relate to what you measured in your coast down experiments?
A lot to unpack there. I want to start by talking about this propulsion cost ratio and why I might have seemed surprised that they were so highly correlated. And the biggest thing is, yes, we are controlling exactly the torque that we apply to each chair. But every chair responds differently. So some chairs are going to be faster, right? They're going to cover more distance and they're going to reach a higher speed. Now, obviously that changes this denominator here, the total distance that it travels, of course. But it also changes the numerator, this total work. So as the speed, as the velocity of the system increases, our work goes up. So if you're just looking at the energy we supply to the system, we're saying we're giving the same pushes to every chair. And if you just look at work, it would seem like the lighter chairs take more work in that maneuver. What work fails to capture is that we also travel a farther distance, right? That's why propulsion cost is useful. But because numerator and denominator both change, it's very hard to predict what differences we're going to see between chairs. The incremental mass study, it took a lot of head scratching. Dr. Spriggle and I both, and we brought it up to Dr. Ferry as well, and kind of just went through some of the possibilities for why this propulsion, how we could control either the numerator or the denominator. And the best possible answer is to go back to a velocity mode where we can hold constant that both the velocity and the distance, right? So now the numerator is half controlled and the denominator is completely controlled. And now the only thing that's left is how much torque each chair requires to attain that velocity or that maneuver. Does that make sense? How much of your question did that answer? Any of it?
A good amount.
Okay.
I'll ask, about how much hair got pulled out in the process too. But so my assumption's a bad one. My assumption's a bad one, but I guess the second question might still be relevant of how these results related to the coast down, because clearly that element of the denominator is still a piece of that equation, right? Propulsion cost is still, that's one part of it, because you're not doing work during that half of the time, but you are contributing distance.
Can you rephrase the question? I didn't quite get.
Didn't you also do these tests didn't you also do component tests or as coast down?
Yes. So in the dissertation, yes, I just pushed the system with the motors completely disengaged too. Just pushed the system and watched how far it traveled in this coast down. I have not run any correlation.
Probably was it a similar story or different story or?
If I remember correctly, yeah, it's a very similar story until you get to the very tight groupings of the final study, the ultra lightweight, folding, and rigid. Those had sort of a discrepancy. We just had a lot of issues with that data collection. But for, easily for the component, the K4, the study 2, easily the coast down aligned with our different metrics here, our propulsion cost, our distance. Not a whole lot of ability for it to align with yaw, but, and I think kinetic energy as well. I think they're all highly correlated. I can go back to that and take a look though. We can talk later.
Hey, Jacob, just out of curiosity, so when you were talking about AIM-3, you mentioned you were looking at tile and carpet. Just knowing that there's a lot of variability in different kinds of carpet, do you think that your results would be generalizable across all carpet, or do you think it's more just for that specific type you're working with?
That's a very good question, and I don't have data on hand to prove or disprove, but you can just sit in a chair. Anecdotally, if I sit in a chair and take it over this low pile, high traffic carpet that you see in, I have one of these pictures here. Yeah, here. This low pile, high traffic carpet, very short carpet. If I run a wheelchair over this, it's going to feel a little more difficult. It's going to be more challenging to travel over this carpet. But if I took that same chair and took it over a shag carpet, that cost, that difficulty is going to skyrocket, right? Because you're sinking into the fibers of the carpet more. You've got to basically part the sea of these carpet fibers with your wheelchair. So I'd expect that your costs would go way up your propulsion cost. Your performance would get a whole lot worse. But in general, the trends might still be there. It's just, as you see with the carpet versus the tile, all of your differences are going to collapse a little bit because it's such a high loss environment universally. You know, your drive wheels and casters, you might still see a difference, but tile is really where that's going to stand out. Does that make sense?
Yeah, it does. Thanks.
Great question. Thank you for that.
Anybody else before we kick the general public off the call? There's a lot to unpack there, I think.
Telling me.
Yeah, all I will say in response to Skylar is never let logic and HCPX code into the same sentence or thought.
One can hope, though, right? I mean, maybe someday.
Yeah. Well, you're young in your career. Why don't you start working on that?
Yeah, but I've had to deal with this for 20 years already.
Yeah, right. No, it is a little frustrating, isn't it? Yeah. A little frustrating. Yeah. Well, thanks. I'd like to invite you all to, of course, come into the lab where we have Sam Adams on tap for everybody. That's why Yogesh is sitting down. No, that's what you missed,
I think the
right?
alcohol you're talking about is hand sanitizer, and I wouldn't.
Yeah, that's right. Yeah. No, I'm sorry everybody couldn't sort of be there in person to sort of celebrate with them a little bit. I imagine there are some people in Atlanta that will run into them a little later. But I appreciate y'all coming on and listening. It was quite a journey for me. I'm sure he looks back and goes, man, I didn't know anything 4 years ago. And I guess that's okay. That's maybe how it should be. All right, I'll ask the committee, the five of us, to sort of stay on with Jacob, and we'll ask him a little bit of other stuff. But thanks again for everybody. Just sort of take care and keep safe.
Yeah, thank you all for attending.
Yeah. That was a pretty big attendance there. That was way bigger than I thought.
Yeah. I'm actually sort of glad that this wasn't in person because I don't know if I could have afforded that much pizza.
Yeah, wow, man, that was pretty good. Yeah, you had a big draw.
The attendance at thesis presentations has been quite high since we went online.
Oh, yeah.
Jeffrey's on
Can you
his
still
phone.
see the recording icon? So I think the record was on. Let's see.